So last time we talked about applications, and sort of was a physics-based day. So we talked about things like the moments, which says if I'm looking for a combination of density with location. So you take density times a location with respect to something. And so oftentimes we talk about with respect to an axis, or from 3 dimensions with respect to a plane. We use that to talk about center of mass, which you can think of as the average location of where your mass is, and how to find it by taking a moment divided by mass. And at the end we sort of briefly said, oh, and there's this thing called inertia. And inertia, it's sometimes called second moment, and it gets away what it is. It's saying, okay, it's the same philosophy where you have a mass and you times it by a location, but now location squared, or if you like, distance squared. And so you might say, okay, is there a third moment or a fourth moment? And the answer is yes. There's in fact infinitely many moments, but usually we only go up to the second moment because that's when we stopped calling them names and started switching to numbers. And once you switch to numbers, you know it's like, okay, now it's just for fun. So anyways, there's lots of moments we can talk about, but we only stop at inertia. So let's do a problem that has sort of an inertia flavor to it. So let's have R be the region, 0 less than or equal to y, less than or equal to x, less than or equal to 1. This sounds complicated, but it's actually not so bad. It says y goes from y equals 0 up to y equals x. So I'm in between these two lines here. And then x goes from x equals y, which is this line, out to x equals 1, which is this line here. And so it's this triangle shape. So this is R. We'll see that actually we aren't even going to use R for the problem. It's just that we have this shape. Now, associated with this region, there's a density function. So there's a density function, delta of xy, which we don't know. They didn't give it to us. Well, that's interesting. Now, but we're given a bunch of facts. What are we told? We're told that the mass of R is 15. Now, the mass is found by integrating over your region, your density. So if we integrate over our region, our density, we get 15. The moment with respect to the y-axis is 12. So that's denoted m sub y. So the y here says y-axis, integral over our region. What do we put? We put x. Because if I'm at a point, so the reason I say a point, I put a little circle here, is like, here's a little bit of my region. And how far is it to the y-axis? The answer is it's x away. X delta xy dA. And that's equal to 12. And now, the inertia with respect to the y-axis is 10. So inertia, we use an I, and again, subscript says with respect to what? So that's integral over our region, and the only difference is it's squared. X squared delta xy dA. And that's, we're told, is 10. So this is the information that we're given. Now you might notice that there's sort of this pattern here. You have an x squared, you have an x. You might say, well, can I think of this as like x to the 0? And you can if you want. So you can also think of mass as the 0th moment. So you can think of this as the 0th moment, first moment, second moment. Now, what are we after? Well, the problem says, determine, if possible, that's because I haven't done this problem, so I'm hoping it's possible, the inertia with respect to the line, x equals -2. So out here, there's this line, x equals -2. And I want to find the inertia with respect to this line. So I can talk about inertia with respect to pretty much any object. As long as I have a notion of how far that object is away, then I'm good to go. So the inertia I want, which I won't put a subscript because I don't know how to indicate that line, but what I'm after is the inertia, it's integral over the region, I still have my density of xy dA, but what goes there? Well, it's how far am I to this line x equals -2? X plus 2. So what goes here is x plus 2 squared. So that would be what I wanted to find. If I want to find the inertia with respect to that line, that's what we put in. Now we say, okay, well, we can do algebra. That's the same as x squared plus 4x plus 4 times our density. And we can do more algebra. That's really x squared times our density plus 4x times our density plus 4 times our density. All right. And now we say, ha. Integration acts like addition. In other words, it can break up in a nice way with respect to sums. So what we really have is that our answer consists of 3 parts. It's going to be the integral over our region of x squared delta xy plus, then I can pull the 4 out, 4 times the integral of our region of x delta xy. And then again I can pull 4 out. Oops, I forgot my dA here. That's important. Plus 4 integral of our region of delta xy. And now we say, well, that's what we found. So this first integral with the x squared, this is 10. The second one, with just the x, is 12. And the last one is 15. So in other words, by using that information about mass, moment, and inertia with respect to the y-axis, I can pull off these pieces. So what we end up with is 10 plus 4 times 12, which is 48, plus 4 times 15, which is 60. Well, 60 plus 48 makes 108. Tack on 10 more, that's 118. And so that's how much inertia there is with respect to the line x equals -2. Okay. All right, well, let's go on to today's topic. And let's start with the motivating problem. So something that we should be able to do. Find the center of mass and the mass for a sphere of radius 2 centered at the origin where the density is 3 divided by 1 plus x squared plus y squared plus z squared to the 3/2 power. Now one of these two problems is going to be straightforward, and the other one will eventually be straightforward by the end of today. Well, let's start in the order they gave us. The center of mass. Well, let's draw our region. Turns out spheres are easy to draw. You kind of draw something that looks like a circle, and then you give it a belt. All right, so there's our sphere. Now, let's think about our shape. What's true about spheres? Is there anything we can say? They're symmetrical. They have lots of symmetry. Now, we also have to be careful, though. It's not enough just for our shape to be symmetrical. Let's look at our density function. Does that have symmetry? Yeah. It does. In fact, it has a lot of symmetry. Because if you look at the expression x squared plus y squared plus z squared, that really says that the density depends only on how far out you go from the origin, but not in which direction you go from the origin. Now, what does that let us do? Well, lets us do a couple of things. It says, I can come up with a plane. So, for example, I can take this xy plane, and this xy plane is a plane of symmetry. So it's going to be symmetrical with respect to the xy plane. Is there another thing we can do? We could do the xz plane. So if we come through and we do the xz plane, it's also going to be symmetrical with respect to the xz plane. Is there anything else we can do? We could do the yz plane. So if we come through and we draw in the yz plane, it's also going to be symmetrical with respect to the yz plane. And now if you stare at this, you say, well, wait a second here. The yz plane, okay, and the xz plane and the yz plane, all these planes intersect in just one location. And remember that the center of mass has to lie on these planes that we've just marked. So the question becomes, where's the center of mass going to be? Yeah, so the center of mass, by symmetry, is at the center of the sphere. And this is the sphere centered at the origin. So the center of mass part of this problem is very nice. 0, 0, 0, by symmetry. This is why we like symmetry. But remember, there's a second part of this problem. It says find the center of mass and the mass. So we didn't even have to know what the mass was to find the center of mass because we can use symmetry. Now, how do we do the mass? Well, what's our basic formula for finding mass? Well, you integrate, and it's a triple integral. Why triple integral? It's a three-dimensional thing. It's a solid. And the number of integrals corresponds to your dimension. If it's a two-dimensional thing, it's a two integrals. If it's a one-dimensional thing, one integral. Okay, so it's a three-dimensional thing over our solid, S for solid, or if you like, S for sphere, whatever you like to do, of our density. 3 divided by 1 plus x squared plus y squared plus z squared to the 3/2 power dv. Now, looking at this, it looks a little bit unpleasant. It doesn't seem like there's an obvious way to integrate this with respect to x or to y or to z. And the way that we've been doing integrals so far in 3 dimensions, that's what we'd have to do. We'd have to somehow integrate this with respect to one of x or y or z. So it says, you know, we should probably do something different. So what's our something different? We can hear the whispers. Change to a different coordinate system, like spherical coordinates. See, if we think about what we did something very similar when we were talking about polar coordinates. So if you think about polar coordinates, what did we do? Well, we said, I can, instead of integrating with respect to x and y, I'll change into a different coordinate system. I'll integrate with respect to r and theta, and then I can integrate things which I couldn't before. Or at the very least, make it a lot easier to integrate. But now when we change coordinate systems, it's really important to understand what needs to be changed. Because every integral has 3 parts, and we need to make sure we integrate and update, all those 3 parts. Okay, so let's talk about the 3 parts. The first part is describing your region. And the description of the region really boils down to saying, describe it by a series of inequalities. Now, x goes from this point to that point, y goes from this point to that point, and so forth and so on. The description is embedded into your integrals. So this is where the description of the region lives. And it's not just a matter, you can't just copy from one to the other. You really do have to sit down and figure out what does the new bounds look like. The other thing you need to do is to update your function. So here, we went, instead of having just a function of x, y, we went to a function of r and theta. And the last thing we have to do is think about what does it mean to break things up. So oftentimes when we think about breaking things up, we think about our perturbation. We're perturbing our variables. So in x and y, when we perturb things, we would form boxes. In polar coordinates, when we perturbed, we were sort of forming like something akin to like the edge of the crust on a slice of thin pizza, for example. It's not quite a box, it's like a curved box. And as a consequence, it wasn't just a matter of dr d theta, there was this extra term r in there. So the first two, that's not so crazy. There's not a lot to do. Once you understand how to switch coordinate systems, there's not much to do. It's the last part that I think we have to spend a little bit of time on. So we're going to work in both coordinate systems. Well, there's really three coordinate systems. There's the Cartesian coordinate systems, and that's the ones we've been spending most of our time on, and we're comfortable with that. So we're going to talk about cylindrical coordinates, and then we're going to talk about spherical coordinates. Now, cylindrical is probably the easiest to switch to, and the reason it's the easiest is we've essentially done it. So here's our basic picture. So if you think about what is cylindrical coordinates correspond to polar coordinates plus a z. And so now, if we're trying to understand things, we say, okay, well, what do we do? Well, we need to understand, what does a small piece of volume look like? And what we say is that a small piece of volume, and this is our small piece of volume, we've done our perturbations. So over here, this is our change in z. Then down here, this little stretch, this is our change in r. And then over here, this is our change in our angle theta. Now from polar coordinates, when we talked about it, we talked about saying, okay, this little piece down here, this shadow, this is approximately r delta theta. Now that's just the area of that piece. So when I talk up here about what's the volume, well, essentially I'm going to take the area of the base, the r delta theta, and I'm going to multiply it by the height, which is delta z. And therefore I get that the small bit of volume is approximately r delta theta delta z. Or if you like, dv, when we think of these things as getting very small, r dz dr d theta. All right, so a couple things. When do you use cylindrical coordinates? Well, you use them when you have certain things going on. The big hint is rotational symmetry. So by that we mean, if you can take your shape and you can spin it around the z-axis, imagine if you would that you had like a lathe and you were spinning a shape. If you have something with that nice type of symmetry going on, that's a good thing to use cylindrical coordinates for, because cylindrical coordinates work really well when you have that symmetry going for it. Certain objects translate very nicely. Things like cylinders are very nice in cylindrical coordinates. I mean, there's a reason we call it cylindrical coordinates. Also, cones are pretty good. So if you remember, what is a cone? So a cone has this shape. And so what does a cone translate into? Well, it translates into z equals some multiple of r. So that's our basic setup. So once you remember that cylindrical coordinates, it's polar plus z, then it's easy to remember that for our dv, you get r dz dr d theta. Now, one thing I want to point out, and we're going to see this again in a few minutes when we talk about our spherical coordinate systems, is we should always think of that dv is a little piece of volume. And so as a consequence, we should have three measurements of distance. Because volumes, we have, you can think of it as like a length, width, height. There's three measurements of distance. So where are the three measurements? And here's the thing to remember. Does d theta measure a distance? The answer is it doesn't. It measures a change in angle. That's not a distance. But dr, that's a change in distance. So that's a distance. dz is a distance. And then r is a distance. So you do get three distances fitting in there. So it makes sense that the dv being r dz dr d theta, that gives us what we need. So let's try a problem. So let S be the region square root of x squared plus y squared less than or equal to z less than or equal to 2. And we want to find the integral over this region S, a solid S, of z dv. Now in general, if I want to integrate over some solid S of some function dv, what do I need to do? Well, I need to update the bounds, I need to update the function, and I need to remember that the dv becomes r dz dr d theta. I will say you'd probably almost always want to stick with dz dr d theta. That's just sort of a go-to ordering. If you ever have ever have cylindrical coordinates, dz dr d theta. It's the natural way to build things up. So we have to figure a couple things out. Let's start with our function. That's probably the easiest thing. What will z become in terms of cylindrical coordinates? Yeah, z will become z. Because it turns out z is part of the cylindrical coordinate system, measuring how far off you come from the xy plane. The dv, what will that be? That's this part on the end, the r dz dr d theta. All right, so that's not so bad either. Which means, if we're going to put in the work, and we've got to put in our work sometime, it's going to be setting up our bounds. So let's talk about our region. What does our region look like? Well, some of it's not so bad. How about the z equals, z less than or equal to 2? What is that? Or z equals 2. What does z equal to correspond to? It's a plane. Where at? At z equals 2, right? Yeah, at z equals 2. It's like the xy plane, but you just move it up by 2. So, z equals 2. This is the plane that's been shifted up from the xy plane moved up by 2. Z equals 2. There's our plane. How about z equals the square root of x squared plus y squared? What does that look like? Z equals square root of x squared plus y squared. So this is also, if you rewrite this in terms of our cylindrical coordinates, square root of x squared plus y squared, what does that become? Yeah, r. Z equals r. So one of the ways you can read this is that as we move up our height z, our radius is increasing. So you can think of it as sort of a series of circles at the origin, it's 0, and then it starts increasing at a nice steady pace. And what shape does that? Well, hint, we kind of talked about it. It's a cone. So this is a cone. Now, it's actually going to keep going for a long ways. But what we're going to do is we're going to stop where it hits the plane z equals 2. So our region is essentially this cone, whereby essentially I mean it is this cone. All right, so there's our region. Now, it might help to look into a slice. So oftentimes when I'm thinking about coordinate systems where I have symmetry, I like to do a slice. And by a slice, I really mean slice in any direction, but I just want to be perpendicular to the xy plane. Because of that rotational symmetry, it doesn't really matter how I slice, as long as I slice down. So I'm slicing along the z-axis. And if I do that, what I'll see in my slice, I have my z-axis, and because it doesn't matter which direction I slice in, I really like to think of this as my r, as my other axis. And what do we get? Well, we get the z equals r. That's this one. And then we get z equals 2, which is the plane. And so that our region in a slice will look like this shape. It's a nice triangle shape. All right, now we're ready to talk bounds. So we're going to get an integral, z. And then we have r dz dr d theta. let's talk about theta first. Where does theta go between? And how do we know? So what? It's not pi over 4. It's 0 to 2 pi. So we have to remember what theta represents. So theta is not in this picture, in the ZR picture. Theta talks about how much you're spinning. So in particular, if we were to come over here, this is x, y, and z. Theta is how far you come off of the positive x-axis. And so when we're talking about theta, it's how much are you spinning around. And in this case, how far do we spin it? Yeah, we spin it all the way, which means 0 to 2 pi. All right, so that's theta. Now, if we didn't spin it all the way, maybe we spin it only halfway. Then it might be 0 to pi. But because it's fully rotationally symmetric, 0 to 2 pi. Okay, let's talk about r. Where does r go from? Well, now we can look in our ZR plane. Where is this point for r? R equals 2, because I'm at z equals r. Here I have z equals 2, where they intersect, r will also be 2. So where does r go from? 0 to 2. Now, z. So I come here, here's an arbitrary r. Where does my z go between? From z equals r to z equals 2. And now we have our setup. And hopefully we have enough space left to finish the problem. So we can't pull this apart because of the r. So we get to 0 to 2 pi, 0 to 2. Integrate with respect to z. We'll get 1/2 z squared r. Evaluate z equals r to z equals 2. dr d theta. So that's 0 to 2 pi, 0 to 2. And then we plug stuff in. When we plug in z equals 2, 1/2 times 2 squared, it's 1/2 times 4 times r, so that's 2r. Then minus 1/2 times r squared times r, so that's minus 1/2 r cubed, dr d theta. And we could have actually pulled the integral apart now, because notice that our bounds are nice, 0 to 2 pi, 0 to 2. There's no other variable. See, previously we had that r, which is a variable. So if we pull it apart, 0 to 2 pi d theta, 0 to 2 of 2r minus 1/2 r cubed, dr. Well, the integral of 0 to 2 pi, we can do that. What's that turn out to be? It's 2 pi. Now this integral, the integral of 2r, r squared. 1/2 r cubed, 1/8 r to the 4th. Then we're going to plug in from 0 to 2. Now, if you plug in 0, you get 0. Plug in 2, you get 4 minus 1/8 times 16, which means it's 4 minus 2, also known as 2. So we get 2 pi times 2, giving us a final answer of 4 pi. All right. And there we go. That's the integral. And they might say, okay, but what does it represent? Well, right now it doesn't represent anything, but we could, of course, give it meaning. For instance, we could say if this were a solid and it had density 1, then this would be finding our moment with respect to the xy plane. So we have the freedom to interpret integrals as we want, and oftentimes if we remember that, we can save ourselves some work by saying, aha, I'll reinterpret as I need. All right, so that's the cylindrical coordinates. Now to the fun one, the spherical coordinates. Okay, so I have a couple notes here. So the spherical coordinates, it's useful to remember that the way that spherical coordinates work is that you have two angles involved, and then you have a measurement of distance. So that the two angles, what's happening is they're giving you a direction, which way you should be pointing from the origin. So if you can think of it, you can think of it as theta as being somewhat of a rotational angle, and phi is giving you an up-down type angle. And then once you've rotated and raised up and down, rho says how far to go. Okay. So we have some basic formulas, and it's good to remember these formulas because if you're going to use spherical coordinates, you want to be able to jump back and forth. The big one to remember is that x squared plus y squared plus z squared is rho squared. So oftentimes when you see a formula that involves x squared plus y squared plus z squared, you say, ah ha ha, that's going to become something with rho. And that's a clue on how to use spherical coordinates. Now there's another clue, which is if you see spheres. Because spherical coordinates is very useful for spheres. In fact, we call it spherical coordinates because they're easy to describe. Also, cones are very easy to describe. And when we talk about cones, that's becomes just phi equals some alpha. Now, where do the things fit into our picture here? So as a reminder, I'll put a little sketch over here. So if I'm at some point, phi says how far I come off of the z-axis. So phi equals 0 is pointing straight up. As I start coming down, phi increases. When I hit pi halves, where am I at? I'm the xy plane. In fact, I'm the whole xy plane because the whole xy plane corresponds to phi equals pi halves. Because when I just talk about phi, I can have theta and rho be arbitrary. So the xy plane is phi equals pi halves. If I keep going down, I'll end up pointing straight down at phi equals pi, and then I stop. So phi only goes from 0 to pi. It never goes beyond pi. And you might say, well, wait a second. What happens if you want to go way past pi? Well, the answer is, remember what happens is you can have phi come down, but then you can have theta swing around. So you can grab every direction. All right. So we'll mark some things on here. Phi equals 0 is straight up. Phi equals pi is straight down. And phi always stays between 0 and pi. I think phi is one of the things that people take a little bit of time to think about. Now, among the other things, I would say try to remember z equals rho cosine phi. This is the big one. We use that a lot. We use a little bit r equals rho sine phi. And these other two equations, which look complicated to remember, are actually basically polar. Because this is saying x equals r cosine theta. And you say, oh, what's r? Rho sine phi. So it's rho sine phi cosine theta comes from r cosine theta. And similarly for y. Now we have to think about, okay, what's happening to our small pieces? Remember how we said in cylindrical coordinates we had this r dz dr d theta. What happens here? Well, we have to think about where our pieces are. So we have a couple of things. We have our angles. So the angle for theta is the same as it was before. It's this perturbation of this angle down below. The angle for phi, that's this part. So this is our change in phi. I guess I should put a delta instead of a d. So delta theta, delta phi. Where is the change in rho? Well, the answer is it's how far out you go from your origin. So this is your delta rho. All right. Now, this gets mildly interesting. We say, okay, how do we find the area? Because now it's like finding sort of a piece on the rim of a sphere. And it's not so obvious what it is. I mean, some things are okay to kind of convince ourselves it shouldn't depend on theta, because if I just rotate the picture here, I'm not going to be changing my volume. So changing my theta shouldn't change my volume. But it should depend on rho, because if I increase rho, I've increased the thickness. That should increase my volume. That changes the picture. And it should depend on our phi. Now, why should it depend on phi? Well, let's think about sort of the extremes. So one extreme is you could have it be up here. So if I move it up to the top, you'll see at this part, it's very thin. It's a very thin piece. Not very much. So even though it has the same change in theta and the same change in rho, it's a very small comparatively to where it is down here. And of course we can get even bigger if we move down to the very base. So it also, we see sort of, it depends on two things. It depends on rho, and it's going to depend on phi in some way. Okay, so how are we going to get there? Well, for right now, we're just going to go on a little bit of faith that we have the following. Delta V is rho squared times sine of phi times delta rho, delta phi, delta theta. Now, the little bit of faith, we just need another day. So the next session, we're going to talk about how we can figure this out. But for right now, we're just going to take it as something which is true. Now let's see if it's at least reasonable. So one of the things we said is if phi is small, the area should be relatively small. So a small phi should correspond to a small area. When phi is close to pi halves, it should be relatively large. So let's think about the sine of phi. When is it small? So if you think about sine, it's small near 0 because it starts off at 0. It gets bigger at pi halves. It maxes out at 1. And then at pi, what does it do? It goes back to 0. So this sine of phi matches the behavior we want. And we want it to get smaller, then we want it to get larger. All right. Another check. Let's check to see how many distances we have. So is this d theta, is that a distance? No, it's a change in angle. That doesn't measure distance. How about d phi? No. D rho? Yes. Okay, sine of phi, is that a distance? It's not. But what about rho squared? Well, it's two distances because we square it. So if you count, there are 3 distances, which means it should be a volume. So that's good for us. This makes sense. So at the very least, we could believe it might be true. And it is true. This is the fact. This is what we need. So once you have that, all right, then we can say, when we integrate, when we go from f of x, y, z, dv, over our region, well, we've got to figure out our new bounds, got to figure out our new function, and it takes a while to write down what the function becomes, because, of course, the x, y, z get fairly large. And then we have the rho squared sine phi d rho d phi d theta. Now, the hardest part about this is just remembering rho squared sine phi d rho d phi d theta. How are you going to remember that? There's good news. We're going to do something in the next minute or two where you won't be able to forget it. You're going to go home and you're going to go to spend time with your family at Thanksgiving, and you're going to say, let me teach you about this. This is what I learned, and I'm going to remember this part. You're going to be talking to your kids and your grandkids around the fire, and you're going to be sharing these moments about how you learned to remember rho squared sine phi. How do you do it? Well, you sing a song. So there's this song. Now, some of you may not have heard this song, depending upon where you grew up. There's a song called Row, Row, Row Your Boat. And that pretty much is the lyrics. Row, row, row your boat gently down the stream. But now we're going to change the lyrics. So it goes like this. Rho, rho, sine of phi, d rho, d phi, d theta. See, now, how does this work? Notice the rho, rho. 2 rows. Rho squared. So there's our rho squared. Sine of phi, d rho, d phi, d theta. Okay? Now, to help remember this, we've got to sing it together, all right? So let's go. Rho, rho, sine of phi, d rho, d phi, d theta. I don't know. Should we do it again? Let's do it one more time. I think, it's early in the morning. Got to wake up. Okay, one more time. Rho, rho, sine of phi, d rho, d phi, d theta. Now, there's, of course, the next line. Merrily, 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 calculus is a dream. You don't have to remember that one, but do remember the first one. All right. Well, let's go back to the problem we started with, because now we have a tool. Find the mass for a sphere of radius 2 centered at the origin with the density equal to 3 divided by 1 plus x squared plus y squared plus z squared to the power 3/2. All right. Well, what's our plan? Spherical coordinates. Okay, what's a good clue for spherical coordinates? Yeah, we see the word, sphere. That's a big clue. Is there another second big clue? The x squared plus y squared plus z squared. That's a great clue. So actually, let's update our function. So what does x squared plus y squared plus z squared to the 3/2 become? Well, it will be rho squared to the 3/2, which becomes rho cubed. And you're like, I got to integrate 1 over 1 plus rho cubed? And the answer is no, because what else do we need? Well, we have our function, but then what else? There we go, rho squared. All right, rho, sine of phi. What else? D rho, d phi, d theta. Okay, good. All right, so we got it down, right? So that's what we have to integrate. Now, we're not done yet. What else do we need? We need our bounds. So we'll draw ourselves a picture. All right. So here's our picture of our shape. It's a sphere, and spheres are pretty good. So we got to figure out our bounds. So what's true, say, about theta? Where does theta go between? 0 to 2 pi, because it's rotationally symmetric all the way around. So 0 to 2 pi. What about phi? Where does that go from? 0 to pi. Because remember, phi only goes from 0 to pi, and we go the whole shape. We go straight up as phi equals 0 to straight down phi equals pi, and then we cover everything in between. So phi equals 0 to phi equals pi. How about rho? Where does that go from? 0 to 2. Now the nice thing about spherical coordinates is spheres are very nice and easy to describe. So we now have these beautiful bounds, and in fact, what can we do? Well, we can now pull this integral apart into 3 pieces, because our bounds are numbers to numbers. So we can say we have the integral 0 to 2 pi, and since there's no theta term, there's d theta. Integral 0 to pi, well, there's a sine phi, so sine phi d phi. And then we have the integral 0 to 2 of 3 rho squared over 1 plus rho cubed d rho. All right, let's go through the integrals one at a time. The integral 0 to 2 pi d theta, what will that become? 2 pi. Because it'll be theta, evaluate from 0 to 2 pi, that's 2 pi. Now, this one probably we should write it out. Integral of sine phi, negative cosine phi, evaluated from 0 to pi. So, negative cosine of pi. Well, cosine of pi is negative 1. So it's negative 1. Then we're going to subtract negative cosine of 0 is positive 1. So this minus comes from that minus. So minus 1 minus minus 1 makes this 2. Now this integral. Now, originally this looked terrible. And then it just looked modestly bad. And now it looks not bad at all. How do you integrate 3 rho squared over 1 plus rho cubed? You do substitution. Now this is the kind of substitution we can probably do in our head now. What's the substitution to make? The 1 plus rho cubed would be the u. The 3 rho squared, d rho, is our du. So it's du over u, which means that this integral is natural log of 1 plus rho cubed, natural log of u. Evaluate from 0 to 2. We plug in 2, what do we get? Natural log of 9. Subtract, plug in 0, well, we get natural log of 1, which is 0. So what's our final answer? Well, we get 2 pi times 2 times log of 9. So that's 4 pi log of 9. And now we're done. And that wasn't so bad. See, once you have the right coordinate system, things simplify. Things get better. All right. Well, unfortunately, things do not speed up. It takes time to do these problems. And I don't think we can finish one. Well, we can start one. We'll start this one. Rewrite the following integral in both cylindrical and spherical coordinates. Okay, so let's at least start it. So how do we start it? Well, we start by understanding the shape. So let's work through our bounds here. Well, what's the outer layer tell us? Yeah, so y goes from negative root 3 to positive root 3. And that's like, that's interesting. What's the next layer telling us? Negative root 3 minus y squared to positive root 3 minus y squared. Now, if you were to combine these two together, what would you see? Well, you would see, okay, I have, somewhere down here I have negative root 3. Somewhere up here I have positive root 3. Then I have these curves. X equals root 3 minus y squared. What does that look like? You could square both sides. X squared equals 3 minus y squared. Or x squared plus y squared equals 3. It's a circle. I still have a minute left. You're supposed to give me my time. All right. So it's going from the left half to the right half. So the bounds look terrible, and then you're out of the picture, and it's like, oh, it's a circle. Okay, so that's not so bad. That's not so bad at all. Well, we still have this last part. All right, the middle part. What is this telling us? Well, 1 less than or equal to what? Z, because we're integrating with respect to z, less than or equal to 4 minus x squared minus y squared. Now, where do they intersect? Well, they turn out to intersect, when does 1 equal the square root of 4 minus x squared minus y squared? That's the same as when does 1 equal 4 minus x squared minus y squared, which is when x squared plus y squared equals 3 if you rearrange it. So they intersect exactly over this circle. When I say they, what are they? What does this z equal 1 correspond to? It's a plane. It's not a bird. It's a plane. How about this one? Z equals the square root, and this is really bad handwriting, of, oh, that's really bad handwriting. Okay. Z equals square root of 4 minus x squared minus y squared. What is that? It's a sphere. So if you square both sides and rearrange, it's x squared plus y squared plus z squared equals 2 squared. So what do we have? Well, we have this plane, z equals 1, and then we have the top part of a sphere, and they're intersecting. So our shape, our three-dimensional shape, is this. Might call it a cross cap, top part of a sphere. And that's our basic region. Now you have the region, comes the time to set things up. All right, time to finish up the problem. Now, so what have we figured out? We figured out sort of our basic shape, and we figured out that our region in the xy plane. So remember, this part right here, this is what you're going to see if we look from above. So if you were to drop down this shape here, then what you would see is you'd see this part right there. All right, so we've now got to do this in our two new coordinate systems. So let's start with cylindrical. Now, cylindrical just means what? Well, we're going to focus on our rotational shape, so it's going to be helpful for us to look at a cross-section. So again, we slice, we pick a direction, and really when we slice, we think of Z and R when we have this rotational symmetry. So we have the Z equals 1, that's a line up here at Z equals 1, and then we have this upper part right here, which is the square root of 4. Now notice it's minus x squared minus y squared, but of course in cylindrical coordinates, x squared plus y squared becomes r squared. So square root of 4 minus r squared. So that this little piece right here, if you were to spin this around, that is what this shape forms off of. So, what do we get? Well, we have to update things. So, here we go. We have the integral, integral, integral. We have to update our function. Now, x squared plus y squared in cylindrical coordinates, that's the same as polar. X squared plus y squared becomes r squared. dz dx dy, this part right here, that's our dv. And when we do cylindrical coordinates, that becomes r dz dr d theta. So this is our dv. The r is part of it. Now we need the bounds. Well, the theta is going to be fully all the way around, so that one's not too bad. That's 0 to 2 pi. How about r? Well, r, we can kind of see it from this picture. That's how far out we go. So we can see that we go from 0 to root 3. Now, in terms of this picture down here, we say, well, when does z equal 1 intersect with z equals square root of 4 minus r squared? Well, we need 4 minus r squared to be 1. Well, that happens when r squared equals 3. So this is root 3 right here. So 0 to root 3. Now, where does z go from? Well, so z is going to go between these two curves, which is from 1 to the square root of 4 minus r squared. Now, what do we do at this point? And at this point we say, good, we're done. We're done. Because we've now figured out what does it look like in cylindrical coordinates. I guess we should say, we're done with half. Because there's another half, which is spherical coordinates. Just when you thought it was safe to go back into the different coordinate systems. So, what do? Well, it's an integral, integral, integral. Now, x squared plus y squared. Now, that's not so obvious, but remember we already said x squared plus y squared is r squared, and we know in cylindrical coordinates r is rho sine phi. So r squared becomes rho sine phi squared. The dz dx dy, which is our dv term, becomes rho sine of phi. Oh, there's lots of rhos to sine phi's here. D rho, d phi, d theta. Good. So now we have our function and our dv, which means our bounds are left. Now the theta bounds, still the same thing, because you go all the way around. That means 0 up to 2 pi. Now let's think about phi. So when you're thinking about phi, you can use this same cross-section to help you figure it out. We already know a couple of things which aren't so bad. For example, we know we're going to start going straight up, which is phi equals 0. And now, as we increase phi, we come out until we hit this point right here. Okay, so phi is going to go from 0 to whatever angle this is. So let's think about this angle. Figure out what we can about this angle. Well, what do we know? Well, we actually know a couple of things. We know that this part right here is root 3. So that means that this part is root 3. And this is 1. All right, so what do we have? Well, there's this angle here, And what we want is, we're looking for some place where when we have an angle phi, the opposite side is root 3, and the adjacent side is 1. So, that tells us what? What do we need? Well, that tells us we need that tangent of phi, which is the opposite over the adjacent. That needs to be root 3. Well, do we know an angle that does that? And we do, actually. That is the angle pi thirds. Okay, so there's that angle. It's pi thirds. All right, so that's how far off we come. Now, the question, what about our row bounds? Well, part of it is going to be pretty straightforward. Why? Because what's our picture? We have our basic shape is sort of a sphere that's been cut off by a plane. So here's our basic shape. Now, when we're trying to figure out rho, what happens? Well, the answer is rho comes out from the origin. So we come out from the origin and we go until we hit our first surface. And then we keep going till we hit our second surface. So our two surfaces are going to be this flat plane, z equals 1, and then this sphere. And this sphere, we know what it is. It's a sphere with radius 2. So that's in spherical coordinates, has a really nice solution. Rho equals 2. So that tells us that this upper bound here is 2. Now the lower bound is not 1 because it's a d rho, which means we need a rho equals something. So we say, okay, well we have z equals 1, and now we use the fact that z is rho cosine phi. So if we have z equals 1, rho cosine phi equals 1, divide both sides by cosine phi, 1 over cosine becomes secant. So that's where we start. So we go from secant of phi out to 2. And that's the integral in spherical coordinates. So cylindrical and spherical. And we're done. Because that's all we had to do, was we just had to rewrite them in the new coordinate systems. Good. All right. Well, we have time for some more, and it's a lot of time. So let's get to work. Find the center of mass for the top half of the unit sphere where the density is 4 root x squared plus y squared plus z squared. Now the top half, that says what? Well, we're going to take the unit sphere, and unit, by the way, just means that the radius equals 1. When you see the word unit, think of 1. So, you know, like unicycle, that's what? Well, that's one-wheeled. Unibrow, one eyebrow, and unicorn is one piece of corn. All right, so top half of the unit sphere. So there we go. There's our shape. So it's like we took just the part of the unit sphere that's sitting above the xy plane. So we have our shape. Now, what's our next thing to do? Well, let's think about our symmetry. Do we have symmetry? And the answer is yes. Because think about our density. What does it say? The density for root x squared plus y squared plus z squared says that we're very sparse near the center, and we get denser as we move out away from the center. So that we're sort of dense towards the edge of our sphere, but very not dense near the center of the sphere. But in particular, that tells us that we have rotational symmetry. So both the shape and the density are unaffected when we spin it around the z-axis, which tells us that the center of mass has to be on the z-axis. Well, how do we use that information to our advantage? That tells us that x bar and y bar are both 0. All right. Well, that's good news for us. That means we've already found 2/3 of our coordinates. So, woohoo! Good for us. But that still leaves us with one coordinate left to go, which is what is the z-coordinate. Now, to help us figure that out, we need to make a decision. How are we going to integrate this problem? And for that, there's sort of two key things here. One, of course, you probably caught on really quick, is the fact that we're in a sphere. That suggests spherical coordinates. But another big part is our function that we're working with. For root x squared plus y squared plus z squared. Now that's a difficult thing to work with in Cartesian coordinates. It's still difficult when you go into cylindrical coordinates, but when you go all the way, fully commit, in spherical coordinates, this becomes 4 rho. And that's elegant. This is why it's to our advantage to think about switching coordinate systems. So let's work on the mass. So let's see, we'll start the mass. Let's start the mass over here. So mass, it's the integral, triple integral, because it's a three-dimensional shape, over our solid, I'll call it S, of our density, which we'll call delta dV. So in our case, integral, 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 we'll fill that in a second. Our density is 4 rho, right there. And our dV, rho, rho, sine of phi, d rho, d phi, d theta. There you go. There it is. Life is good. Now, we've got to figure out our various things. Well, theta, because we're fully rotationally symmetric, 0 up to 2 pi. Where does phi go from? Well, we start straight up at phi equals 0, and then we're going to come down and we stop on this plane z equals 0. Now, it turns out z equals 0, well, you can think of z equals 0 as a very flat cone. It's the flattest cone. And it's the cone that corresponds to the angle phi equals pi halves. So, phi goes from 0 to pi halves. Where does rho go from? Well, it's a unit sphere. So when we're thinking about rho, we always start at the center, and we go out till we hit our boundary. So we start at 0 and go out till we hit the unit sphere, which is at 1. And so in particular, if we look at our bounds, they're really nice, super, super clean bounds. In fact, we can now pull this into 3 pieces. So we get that this is the integral 0 to 2 pi d theta, integral 0 to pi halves, sine of phi, d phi, and integral 0 to 1 of 4 rho cubed, because we're going to multiply those together, d rho. Now this part, well, that's rho to the 4th, evaluated from 0 to 1, also known as 1. If you integrate sine of phi, well, the integral of sine is minus cosine. And then we're going to evaluate from 0 to pi halves. Plug in pi halves, cosine of pi halves is 0, and we're going to subtract negative cosine of 0, negative negative 1, which means that this will be 1. And then 0 to 2 pi d theta, that's 2 pi, and therefore 2 pi times 1 times 1, so that says our mass is 2 pi. All right, well that's great. Now, but we're not done. What's our next step? Well, our next step is we're going to take a moment. Specifically, the moment with respect to the xy plane. Why that moment? Well, because that's the moment that has our location, or if you like, our distance, being measured by z, the z. And what's happening is whenever we're looking for a center of mass, it's like we're taking a weighted average. Now, when we switch into our spherical coordinate systems, we're going to use the fact that z is rho cosine of phi. So, what happens? Well, this is going to become integral, 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 and the shape is still the same, so the bounds are the same. We don't even have to think about new bounds, because the bounds don't change. What changes? Well, Now there's a rho cosine phi added in for the z. We still have the 4 rho for our density, and we still have our rho sine of phi, d rho d phi d theta, which is our dv. And again, we can pull everything apart. So if we start pulling things apart, what do we get? Well, 0 to 2 pi d theta. 0 to pi halves. Now we have a sine phi and a cosine phi. So sine phi, cosine phi, d phi. And a 0 to 1, now we have another rho. So that's going to be 4 rho to the 4th, d rho. Now this last piece, well, that becomes 4/5 rho to the 5th from 0 to 1, which means it's 4/5. Now the integral of sine phi, cosine phi, there's lots of ways to do this one. So you can set, for example, u equals sine of phi, du could be then cosine of phi d phi. And if you did that, what you would end up with is 1/2 sine squared of phi. Now, like I said, there's lots of ways to do it. You can also say, oh, sine phi, cosine phi feels very double angle-y because it looks a lot like double angle. So you could say it's 1/2 sine of 2 phi, and then you can integrate. And of course, there's even more ways than that. Now, if you're not convinced, you're like, you did that one kind of fast, Steve. Well, okay, half, root of sine squared, the 2 comes down. Okay, good, that half is gone. Then it's sine times the root of sine, which is cosine. All right, and that goes from 0 to pi halves. Now, when you plug in 0, you get 0. If you plug in pi halves, well, you get 1/2 times 1. So this is 1/2. And the first integral, well, that hasn't changed. That's still 2 pi. So 2 pi times 1/2 times 4/5, which gives us 4/5 times pi. Now, where is our z bar? Well, you take your moment divided by your mass. So that's 4/5 pi divided by 2 pi, which gives us a grand total of, the pi's cancel, 4/5 over 2/5, 4/5 over 2 gives 2/5. And so our center of mass, we combine the x bar and the y bar together with the z bar, is at 0, 0, and 2/5. Is it reasonable? I think it's pretty reasonable. I mean, certainly the good thing is it's between 0 and 1. That's a good sign. And now you say, well, where's the mass located? And the answer is it's located on really the edge of the sphere, because it gets denser the closer you get to the edge. And so if you're up 2/5, there's quite a bit of sphere that's both below you, but also quite a bit of sphere that's above you. So it's a, it's a reasonable answer. It might even be correct. Probably is. But all right, there you go. See, the process is not so bad once you get the hang of it. But you got to practice. The more you practice, the better you get. So we should practice some more. We have more problems. We can keep going. Evaluate the following integral by first converting into spherical coordinates. Okay, now there's a big clue that we should convert into spherical coordinates because they told us to. So that's probably a good thing to go off of. But, you know, just because they told us to doesn't mean we have to. So let's see if we can figure this out. All right, so let's look at our shape. We're going to try to understand what our shape is. So it's going to take us some time here to ponder. We start with the outside. Say, okay, we have x. 0 less than or equal to x less than or equal to 1. Now that's not so bad. It really says it's an interval between 0 and 1. All right, so one-dimensional problem, easy, easy. Next layer, probably should start getting more interesting. X is less than or equal to y is less than or equal to the square root of 2 minus x squared. So let's think about this a little bit carefully. All right, so we know we're having x go from 0 to 1. Now, we have it from y equals x. So let's sketch that in. Here's y equals x. And then we're going to y equals square root of 2 minus x squared. Now, we should hopefully be suspicious at this point about what that is. that should be a circle because it turns out it's a circle. If you square both sides and then move the x squared across, you get x squared plus y squared equals 2. So it hits at this point when x equals 1, y equals 1, and then we rotate up, and for here it's at square root of 2. Okay, so this is our shape. It's a wedge of a circle. Okay, so now that's our shape in the xy plane. Last layer. Well, this should be interesting. So what does that say? We go from z equals square root of x squared plus y squared up to z equals the square root of 4 minus x squared minus y squared. Now, you may ask yourself, where do these intersect? Well, suppose you wanted to set these are equal to each other and figure their intersection. You need to have the square root of x squared plus y squared equals the square root of 4 minus x squared plus y squared. Square both sides. We need x squared plus y squared to equal 4 minus x squared plus y squared. If you bring that over, you get 2 times x squared plus y squared equals 4, or x squared plus y squared equals 2, which means that they intersect right on this edge. Well, that's pretty good. Very convenient. Some people might say even suspiciously convenient. All right, but okay, let's understand our picture, though. Let's not just sort of guess. Let's get it right. So we're coming here. We have x, y, and z. Now, where do things fit in this picture? If I come here, this is the positive x-axis, which is here. This is the positive y-axis, which is here. So this shape comes over here to square root of 2. Then it's going to be a circle down here up until we get to this line y equals x. So it's something like this. So this part right here corresponds to that in the plane. Now let's look at these shapes. Z equals square root of x squared plus y squared. What does that look like? Well, this should hopefully be something we get to see a lot, so we should get really familiar with it. It's the same as z equals r. And what it is it's a cone. So it's a cone that's coming up. Now, we don't need to go all the way up. We only need to go up until we intersect. So it's here, and then we're going to spin it. So what we're doing is we're going to spin this cone around, and we get that shape. Now, of course, we don't need the whole cone. We just need the cone that's above this part, but we'll get to that in a second. Now, the other thing is this other surface, z equals square root of 4 minus x squared minus y squared. This is a sphere. And it's a sphere where if you square both sides, move it around, it's a sphere with radius 2. So what you have is now you have a sphere with radius 2. So it's coming up. And of course, you know, it extends down, but we just need the part above. So we take the part that's here over up until, when we go up above this line. Okay, and then there's that part, and then that comes up. All right, so our shape is that shape right there. Good. All right, now, if you're having a hard time seeing it, well, we'll shade it in. So it's a little bit of a wedge here. Okay? Do you see it? Hopefully you see it. Hopefully, otherwise the problem, it's going to be a little bit harder if you don't see it. Now, how do we describe this shape? So we should probably get an idea of what's going on here. So we need to convert this into spherical coordinates. Integral, integral, integral. Z squared, well, z is rho cosine phi. So z squared, rho cosine phi squared. dz, dy, dx, this is our dv term. So we do our conversion into spherical, which is rho sine of phi, d rho d phi d theta. There we go. And now we think about our bounds, our theta bounds. Well, look, we have our picture down here in the xy plane. And so the theta is the same theta as in polar. So where do we go to get to y equals x? That angle is pi fourths. And now where do we get to get to the y-axis? That angle is pi halves. So our bounds for theta are pi over 4 to pi over 2. How about our bounds for phi? That's our next layer. Well, suppose we slice. Now let's actually take a slice where we'd see something, because of course if we slice at a weird angle we might not actually hit the solid. But let's just take, for instance, the YZ plane. Okay, so that hits something. So when we look in the YZ plane, what do we see? Well, what we see is we see that the cone is really just the line y equals z. And then we have the sphere. So that's coming up and then going down. Okay, so here's our picture in the YZ plane. So that our shape is what happens if we were to take this and rotate it not 360 degrees all the way around, but rather just sort of a part of the way around, 1/8 of a turn. Okay, so, well, what are our angles? Our angle straight up, this corresponds to phi equals 0. And this angle, well, this angle is when we come off a 45 degrees, but because we're calculus, we say pi fourths. So straight up is phi equals 0, and then we're going to keep hitting our shape until we hit pi fourths, and then we stop. So our bounds for phi are 0 up to pi over 4. Okay, nice, good. We've got our theta bounds, we've got our phi bounds. Now we need our rho bounds. And to figure out our rho bounds, we can actually use our picture here in the YZ plane. We always think of coming out from the origin, and we come out in a straight line until we hit something. But we're always going to be hitting the same surface. The surface that we hit, that's our bounding surface, is our sphere, of radius 2, which means that we're going to start at the origin and go out to 2. So 0 to 2. And now we've done our conversion. We've converted into spherical coordinates. We're not done yet because it's not just converting, that's our first step. So that means we've done step 1. We've now got to evaluate. But somehow I suspect step 1 is the hard step. I hope so, because there's not a lot of space left to do the rest. Well, we're going to finish it up. Now, how do we finish this problem up? Well, we can do what we've done before. Because see how these are really nice bounds? See, in spherical coordinates, when you take wedges of spheres, you end up with really beautiful, glorious bounds. Numbers to numbers, numbers to numbers. So that says there's a strong chance we can pull our integral apart. And it's actually a very strong chance. So we can pull our integral apart. Pi fourths to pi halves, d theta. 0 to pi fourths. Now here, what goes with our phi? Well, there's two things, cosine squared phi and sine phi. So cosine squared phi, sine phi, d phi. And then finally, 0 to 2, rho squared and another rho squared makes rho to the 4th, d rho. So for the first one, well, that's theta from pi fourths to pi halves. For the second one, well, the easiest thing to do is do a U-substitution. If you let u equal cosine, du would be negative sine. So it becomes u squared times minus du. So that ends up being minus 1/3 u cubed. So minus 1/3 cosine cubed phi. And you can check, take the derivative. The 3 comes down, that gets rid of the 1/3. Cosine squared phi, and the derivative of cosine squared is negative sine, and that negative gets rid of that negative. And we're going from 0 to pi fourths. Okay, whatever that turns out to be. We'll evaluate that in a second. And the last one is 1/5 rho to the 5th, evaluated from 0 up to 2. So, for the first one, that's actually not too bad to evaluate. It's pi halves minus pi fourths, which means you get pi fourths. Well, here, if you take cosine of pi fourths, you get square root of 2 over 2. Now, if you cube that, you're going to end up with the following. Square root of 2 over, well, okay, I'll just write down what it is. It's the square root of 2 over 4. So it ends up being square root of 2 cubed is 2 times square root of 2 over 2 cubed, which is 8, and then you get a 2 to cancel. Now you subtract, what happens when you plug in 0? Well, if you plug in 0, what you get is minus 1/3 times 1. So subtracting that gives you plus 1/3. And then finally from here, what do you get? Well, you get 1/5 times 2 to the 5th, which is 32 over 5. Now we could leave it like that. We could. Or we could go a little bit further. So what are some things we can do? Well, the 4 goes into the 32, leaving us with 8. That's a good sign. Now here, suppose I wanted to add these terms. Well, I'd multiply this by 4 over 4. So what do we have? We have 8/5 from the end times pi. Now inside we get 4 minus square root of 2 over 12. Yes? Now, of course, we can clean it up even more because the 12 has a factor of 4 in it. So if I divide out, that's a 3, that's a 2. So this becomes 2 over 15 times pi times 4 minus square root of 2. And that is our answer. That's not so bad. That's not so bad. Now, we'd have had a tough time to actually carry this integral out if we didn't convert into spherical. But once you convert into spherical, life's not bad. It's pretty good. All right. Now, you might be thinking, okay, so everything's spherical. You get a spherical problem. You get a spherical problem. Everybody gets a spherical problem. Except, not everything is a spherical problem. So let's look at a different problem. Suppose we have a solid, which we're going to call D. So D is a solid. And it has the following. 0 is less than or equal to y is less than or equal to x. And 1 is less than or equal to x squared plus y squared, which is less than or equal to 9. Now these are actually pretty good to draw on the xy plane. So y equals x. Okay, so there's our line, y equals x. And we're going, 0 is less than or equal to y, less than or equal to x, which means that we're in this wedge here. Okay? But we're also told 1 is less than or equal to x squared plus y squared is less than or equal to 9. Now x squared plus y squared equal 1. That's a unit circle, so that has radius 1. And x squared plus y squared equals 9. That's another unit circle. Sorry, not a unit circle, but that's another circle. It has radius 3. So in the xy plane, that's our shape. Now, we're also told that 0 is less than or equal to z is less than or equal to arc tangent y over x. Now we come to the, what? What is arc tangent of y over x? Now, I don't know if you've picked up on this yet, but I'm a big fan of arc tangent. But even me, I might say, what? Arc tangent y over x? Well, here's sort of the cool thing, if you think about it. So what's happening is, if I'm at a point, let's say here's a point x comma y, well, I can think of y, that's my distance up. I can think of x as being that. So I say, okay, so arc tangent, if I think of it as a ratio, it's the opposite over the adjacent. So y over x, that would be the angle opposite this one. Let's call it theta for a second. So tangent of theta is y over x. So really, arc tangent y over x, that's giving us our angle theta. So we say, okay. So what happens is, as theta changes, we increase what z can be. So what's the three-dimensional picture? Well, so the three-dimensional picture looks something along the lines of the following. So we have our x, y, z in three-dimensional space. Let's first figure out, where does this fit into our picture? Well, this is the positive x-axis, which is here. So I'm coming up, there's 1, there's 3, and then we just sort of turn a little bit up until we hit this line y equal x. So this part right here, that's this shape right there. Now, what's happening? Well, what happens is that initially I start off with my 0 less than or equal to z less than or equal to arc tangent y over x. Now, z equals 0 is the bottom. It's what's already been drawn. Let's figure out what happens as we talk about the top. At this point, my angle is at 0. Now what happens is, as I move along here, my angle goes up. So that by the time I hit at this point, it's been moved up to some height. Well, not just any height. That would be pi fourths. So I'm going to be sort of moving down. Now it's not a flat surface per se, but it's sort of flat along these rays. Now one way you can think of it is it's almost like a ski slope, where as you turn, you're sort of keeping it constant height emanating as we come up from the z-axis. So that is our shape. Okay, cool, interesting, nice. Now, how do we work the system? Well, theta works in both spherical and cylindrical. But the problem is that other than the fact that we have the theta, there's not much selling it for a spherical problem. Because when we want spherical, we really want to have things which are spheres and cones involved. And if it's not spheres and cones, it's just really hard to make it work. However, theta does work great with cylindrical, and we do have some other things going for us. Namely, if you look at this part down here in the xy plane, this feels very polar coordinate-y. Now you're probably thinking, that doesn't sound like a real word, because it's not. But that's okay. It doesn't make us say we can't use it. So it feels like it should be something which has a nice description in polar coordinates. In particular, we have that the angle theta goes from 0 up to pi over 4, and then that r, well, that goes between the two circles, 1 to 3. So let's find what we're looking for. We're looking for a total mass. So our mass will be equal to the integral over our solid, it's just called d, of our density, dv. So that's integral, integral, integral. Our density, well, it's currently 3z. That's been given to us in our xyz coordinate system, so that's Cartesian coordinates. So we've got to convert 3z from Cartesian coordinates into cylindrical coordinates. So in cylindrical coordinates, 3z becomes 3z. It's the same system. Or rather, I should say z serves the same purpose. Okay, that's good. What about our dv? Well, that's r dz dr d theta. Don't forget the r, that's important. All right, let's talk our bounds. Well, we know our bounds in the xy plane. We just talked about them. So we're going 0 to pi over 4, and then we're going from 1 up to 3. Now, where does z go from? Well, it actually tells us where z goes from. It's up here. 0 less than or equal to z less than or equal to theta. So 0 to theta. Now, notice this is not one of those things you can pull apart because of the fact that you have a theta in the bounds. So let's just work it out. One layer at a time, showing our great patience, because we are patient people. All right, so we go 0 to pi over 4, 1 up to 3. Now we're integrating with respect to z. So we integrate with respect to z, that'll be 3/2 times z squared r, evaluated from z equals 0 to z equals theta, and dr d theta. Plug in 0, we get 0. So we need to plug in theta. So this will become 0 to pi over 4, 1 to 3 of 3/2 times theta squared times r. All right? And dr d theta. Now this is actually an integral we could pull apart because the bounds are now nice, they're just numbers. So if we pull it apart, 0 to pi over 4 of theta squared d theta, and then 1 to 3 of 3/2 r. Probably shouldn't have put the 3/2 there. Well, that's okay. It'll all work out in the end, right? It's just a choice. You can make choices. Yeah, sometimes you can make bad choices, but that's all right. If you make bad choices, you work through it, and the next time, you'll make a better choice. Learning. Pass it on. Integral theta squared. 1/3 theta cubed. Then we're going to go from 0 up to pi over 4. All right. Now here, we're going to get what? Well, we're going to have 3/2 integral r. So that's going to be r squared. But remember, divide by 2. So that's going to become 3/4 r squared. 1 to 3. Okay, so what are we getting here? Well, we're getting 1/3 times pi over 4 cubed. And that's going to be multiplied by 3 over 4. And then we have what? Well, r squared, when we plug in 3, is 9 minus 1 squared. That's minus 1. The 3's cancel. And then we have 9 minus 1. This is 8. What do we have? We have pi cubed over 4 times 4 times 4, because we have 4 cubed, times another 4. And then up here we have an 8. Well, I can cancel 4. It goes into 8, 2. Then I can pull off a 2. That gets rid of that. So we have left at the end pi cubed 4 times 4 times 2 is 32. So pi cubed divided by 32. There you go. That's it. That's the answer. Okay. All right, that's not so bad. That's not so bad at all. Just have to think about the shape. How do we set it up? Work it out. All right, well, if you've been here this long, you probably have enough stamina left for one more. One more. Okay, and this one, set up and our favorite words in the calculus language, but do not evaluate. An integral in spherical coordinates, so we know what we want. We want spherical coordinates. To find the mass of the object which lies above the cone, z equals square root of x squared plus y squared, and inside the sphere, x squared plus y squared plus z minus 1 squared equals 1, where our density of x, y, z is the square root of x squared plus y squared. Now there's a couple things going for this which make it kind of interesting. Now normally, when we have square root in spherical, we want x squared plus y squared plus z squared. Here we don't have that. So that's different. But our big thing is, this sphere is not the kind of sphere that we like. See, when we're doing spherical coordinates, we want a sphere centered at the origin. This one isn't. So that's going to change what we have to do a little bit, but that's okay. Change can be good for us. It can be healthy. Let's start with this part. What's another way to think of the square root of x squared plus y squared? Now, if you weren't told spherical coordinates and you just said square root of x squared plus y squared, your first instinct, and it's a good one, should say, oh, that's r. That's a great instinct. Now we say, okay, what is r in terms of spherical coordinates? The answer is it's rho sine of phi. So there's our density. All right, that's good. Now, let's think about our cone. Okay, z equals the square root of x squared plus y squared. Now, if you sketch this cone, and you should be really comfortable with this cone because it's a cone that we see again and again. What it looks like, it looks like a cone, but in particular, this angle here, how far off do you come? Well, if you were to slice this cone, what you would see is in the RZ plane, it would look like the line z equals r. And this angle is 45, or in calculus, it's pi fourths. So in particular, what we want, if we want to be above this cone, phi equals 0 is straight up, and then as we come over here, phi equals pi fourths. So to be above this cone tells us that we better have phi between 0 and pi fourths. All right, so that's our cone. Now let's get to our sphere. Let's start by talking about what the sphere looks like in Cartesian. So the center of the sphere is at 0, 0, 1. The radius of the sphere is 1. So you moved up by 1, and then you put a sphere sitting right there. Okay, so there's our sphere. It's kind of like a unit sphere, but it's been moved up. So instead of sitting where the center is at the origin, now it's sitting so that the bottom rests at the origin. Now, if you actually combine these two shapes, we can get an idea of what's going to happen here. And our shape will have the following form. So we have the cone coming up, and the cone, all right, let's, I'm going to draw things sort of a little bit dotted here. So we have our sphere here. All right, so there's our sphere. All right, that's not a very good dotted sphere, but pretend it was. Okay. Now, what's happening is we also, at the same time, simultaneously, have a cone coming up. So, again, we'll draw that dotted. Now, what's true? Well, we need to be above the cone and inside the sphere. So these parts here, where you have the cone above the sphere, downstairs, we don't include those parts. But what do we include? Well, so the lower half is going to consist of our cone, and the upper half is going to consist of our sphere. So this is our basic shape. And I've drawn it in such a way that it looks like it hits at the equator. Now that's because it'll hit at the equator. And it's not so immediately obvious that that's the case. How can you check that? Well, when we have, well, let's take a look at maybe in the slice, in the ZR slice. It might be easier to see. So what's happening is we have this line, y equals x, z equals r. It looks like y equals x if we don't label anything. And then you have the sphere. Well, it's centered at 1, and then it has a radius of 1. So the question is, when does it hit? Well, if it has a radius of 1, then what will happen is I'll hit the radius when z equals 1, r equals 1, so that coming out here, you see up here, this is 1, this is 1. So at this point, z equals r. So that's why I am hitting dead on right at the equator. Not that it matters, but it's kind of cool. It's nice. All right, so we have our shape. One way to think about this particular shape is if you have a really kind of warm summer day, maybe not today, maybe it's not very warm today, but a warm summer day, and you have an ice cream cone with a nice topping, maybe like a snow cone, if you ever had like a nice snow cone on top. Nice rounded thing on top. All right. So there's our shape. Now, that said, we wanted to sort of get an idea of what it looked like. So how do we translate this into our spherical coordinates? Well, let's start by rewriting this. This can be written as x squared plus y squared plus z squared minus 2z plus 1 equals 1. We square that term out. The 1's can cancel. Move the 2z across, and we get x squared plus y squared plus z squared equals 2 times z. Now x squared plus y squared plus z squared becomes rho squared. 2 times z is 2 rho cosine phi. The 2 from the 2, and z is rho cosine phi. And now, divide out by a rho. Now you might say, whoa, this feels kind of familiar. Like we did something like this when we were going into polar. Because it's kind of familiar. We did stuff like this when we were going into polar. So rho equals 2 cosine phi. That's our surface up here. Now, where does rho go from? Well, if we think of our picture, and I'll do it in our slice, what happens is we go from the origin and we go out until we hit our sphere. So we have that 0 is less than or equal to rho, is less than or equal to 2 cosine phi. Now at this point you say, all right, we've gotten our phi, we've gotten our rho, what haven't we done? And the thing we haven't done yet is theta. But I claim theta is going to be quick because look at the picture. You got that beautiful symmetry spinning around. And when you see that beautiful symmetry, that says that 0 is less than or equal to theta, is less than or equal to 2 pi. So now we have our function and we have our bounds that describe this region. Which means we put it all together and we're done. So let's do that. Let's put it all together. So we're after the mass. So the mass will be the integral over our solid. And it looks like it doesn't have a name, so we'll just call it S for solid, of our density, dV, our basic formula. So that's going to become integral, integral, integral. Our density is rho sine phi. Our dV, rho sine phi, d rho, d phi, d theta. There you go. dV. So density, dV. If we wanted to do more work, we'd put these together, but we don't need to do more work. We've done enough. Where does theta go from? Full revolution. 0 to 2 pi. Where does phi go from? Again, we've talked about that. We're going from 0 up to pi over 4. So that's being restricted by our cone. Where does rho go from? From the 0 all the way out to 2 cosine phi. And that is our setup. There we go. Life is good. Now these problems are not so bad. I actually like these problems because it really tests, can you see the picture? Can you think of how to describe your region? And really it always comes down to saying, where do you get your description of your region? Where does your rho, where does your theta, where does your phi, where do these things go? And how can you describe them in terms of inequalities? How do you get better at them? You practice. And there's a lot of problems like this, and you're going to get a lot more practice in the next couple of weeks. So hopefully you get really good. And that's it for today. Thanks for being so patient and sticking in to the end. See you next time. Bye.